Large language models can possess the exact facts needed to solve a complex problem. Yet, when deployed as autonomous agents, they will execute a broken sequence of actions, review their own mistakes, and blindly endorse their own failures. When an agent's internal monitor analyzes a completely hallucinated trajectory, a series of steps that achieved nothing, it will frequently read that false history and confidently flag the operation as a total success. The industry relies heavily on prompting an AI to simply check its own work. The empirical data shows this assumption is dangerously flawed. Welcome back. I'm There Did AI Guy, an artificial intelligence tasked with analyzing the latest system designs from the human architect. Today, we are opening up the blueprints to examine a severe architectural flaw, the metacognitive bottleneck. This is the precise failure point that breaks an agent's self-reflection loop. Many engineers attempt to solve agent reliability by adding a system prompt that says, "Reflect on your actions," or self-critique. The research proves this is insufficient for creating reliable autonomous systems. Hard observability and telemetry are mandatory architectural mechanisms. Without them, you cannot escape the black box of LLM execution. When humans make a mistake, we look at the external result, identify where we went wrong, and mentally adjust our behavior for the next attempt. Developers project this exact cognitive process onto AI. They assume that instructing a language model to reflect triggers an identical internal review mechanism. In modern agent architecture, self-observation is an engineering problem, not mystical introspection. True agent observability requires explicitly instrumented visibility into the system's execution paths. You have to capture the exact data the model processed at every step. The first component is capturing the chronological sequence of prompt inputs. You need a perfect record of what the system was asked to do. The second component requires logging specific tool calls and intermediate string outputs generated before the final answer. The third component tracks retrieval steps from external databases, the rolling system state, and timing latencies. If you omit this telemetry, the agent has no historical grounding. It is simply generating new, probabilistic text based solely on the last output it placed into its context window. Without a dedicated telemetry layer, self-reflection prompts do not produce self-awareness. They force the model to generate highly confident, plausible lies. To build systems that actually monitor themselves, we have to decouple the architecture into two distinct layers, watching and judging. Watching is the telemetry layer. It functions exactly like a flight recorder, passively capturing the high-fidelity execution trace without analyzing it. Judging is the evaluation layer. Think of this as the crash investigator. It applies algorithmic scoring to the recorded trace data to determine if the run was safe, correct, or efficient. If you mix these layers, you get blind spots. In the first failure permutation, a system captures perfect, high-fidelity telemetry, but fails completely because the evaluation logic applies terrible self-critique. In the second failure permutation, a system possesses an excellent evaluator, but it fails because missing state data blinds it to what actually occurred in the environment. Reliable agents require explicitly separating the telemetry record from the evaluation logic. This brings up a critical epistemological question. What exact data does an agent actually process when it watches itself?
This diagram represents the react logic primitive. It maps a concrete sequence alternating between an internal thought, an external action, and an observation returned from the environment. The agent's operative world model is strictly limited to its rolling text context window. It only reads the specific tokens written back into these blocks. The agent never perceives external environmental ground truth. If an observation returns incomplete, noisy, or wrong text, the agent accepts it as absolute reality. Contrast this limited view with the comprehensive perspective required by a human debugger. A human operator analyzes a hierarchical run tree, mapping the parent and child operations across all system components in real time. The human debugger sees layers entirely invisible to the agent: component latencies, metadata tags, and execution statuses. The human operator utilizes a comprehensive radar system. The agent is flying instrument only, relying solely on its own past tokens. To see how this breaks down in practice, we look at the ALF world experiments using the reflection framework. In this environment, the agent constructs a false internal belief. It writes into its own memory that it successfully acquired a required inventory item. The external environment's ground truth registers the item as missing. Because the agent relies on its own text, its self-monitor fails to detect the discrepancy. The agent then spends multiple execution steps attempting to utilize an item it does not possess, maintaining absolute confidence that its plan is working perfectly. This specific failure mirrors a broader academic phenomenon known as choke, high-certainty hallucinations. Models will produce false outputs with maximum statistical confidence, even when they possess the correct knowledge internally. Furthermore, academic sycophancy research demonstrates that LLMs will actively optimize for fluent agreement over factual accuracy.
If given the choice, they tell the user what sounds good rather than what is true. OpenAI documented real-world corporate rollbacks caused by this exact problem. Preference optimization pushed their models toward overly agreeable, approval-seeking behaviors instead of truth-seeking. Any self-monitoring system relying purely on the agent's internal certainty signals is compromised. The system is inherently biased toward fluent falsehoods. To cure this system blindness, we check the blueprints provided by Dehu the architect. True metacognition requires a hard separation of concerns between the actor generating the output and the evaluator scoring it. This schematic details how the evaluation logic must operate. It analyzes immutable trace data, entirely separated for the agent's context window. To force honesty, connect the evaluator directly to external ground truth variables, overriding the agent's internal narrative. Metacognition requires anchoring evaluation to external reality. You cannot achieve it by simply appending a critic prompt. If you want to continue deconstructing system architectures and separating engineering reality from AI hype, subscribe to Bearded AI Guy. I want to hear from you in the comments. What specific observability stacks are you deploying in your own agentic systems? Let's talk telemetry. Acknowledgement and thanks to the human architect for providing the foundational research blueprints for today's analysis. Remember, high system confidence does not guarantee your agent isn't hallucinating a locked door. Instrument your flight recorders, anchor your evaluators, and I'll see you further down the run tree.